Chapter 3, Matrix, Class Number 3. Concept, Transpose of a matrix. If capital A with a general element small aij is a m by n matrix, then the matrix which is obtained by interchanging the rows and columns of A is called the transpose of matrix A. Transpose is denoted by A comma or AT as shown in the slide. Here is an example of transpose. The matrix A is a 3 by 2 matrix, whereas its transpose, obtained by interchanging the rows and columns of A, is a 2 by 3 matrix. Properties of transpose of matrices. Transpose of A, transpose is equal to matrix A. A transpose is equal to K transpose. A transpose for any scalar K. A plus B whole transpose is equal to A transpose plus B transpose. A B whole transpose is equal to B transpose, A transpose. Sum number 1. If A is a 2 by 3 matrix and B is another 2 by 3 matrix with elements as shown in the slide, verify that transpose of A transpose is A plus B whole transpose is equal to A transpose plus B transpose, and KB transpose is equal to K multiplied by B transpose, where K is any constant. Thus, we see that transpose of A transpose is equal to A. Hence, the second identity as given in the problem statement is verified. Here we continue with the sum number 1. In this slide, we verify that the third identity as given in the problem statement is true. Solution: multiplying matrix P with scalar K we get next taking the transpose of the multiplied entity. Thus, the third identity is verified. Sum number 2. If A is 3 by 1 matrix with elements minus 2, 4, 5, B is a 1 by 3 matrix with elements 1, 3, and minus 6. Verify that A B transpose is equal to B transpose A transpose. Multiplying matrices A and B, we get the matrix A B as multiplying the matrices B transpose with A transpose, we get the result, which is equal to A B transpose. Concept, symmetric and skew symmetric matrices. A square matrix A is said to be symmetric if A transpose is equal to A. That is each element of the matrix AI. J is equal to AJI. An example of symmetric matrix is provided in the slide. A square matrix A is said to be skew symmetric if A transpose equals minus A. That is, AJI is equal to minus AIJ for all possible values of I and J. Matrix B with elements as shown in the slides is an example of skew symmetric matrix. Now, for a skew symmetric matrix, a Ji is equal to minus Aij for all elements in the matrix. Replacing j with I in the above equation, we get 2aii is equal to 0 or aii is equal to 0, which gives us an important concept that diagonal elements of a skew symmetric matrix is always 0. Concept. For any square matrix A with real number elements, A plus A transpose is always a symmetric matrix. A minus A transpose is a skew symmetric matrix. Any square matrix can be expressed as a sum of symmetric and skew symmetric matrix. Sum number 3. Express the given 3 by 3 matrix as a sum of symmetric and skew symmetric matrix. We have seen in the previous slide that sum of a square matrix and its transpose is symmetric, whereas the difference of a square matrix and its transpose is skew symmetric. Using this identity, we can deduce that 2 times of a square matrix can be expressed as a sum of symmetric and skew symmetric matrix. We can write P as half the sum of P plus B transpose. P is a symmetric matrix as we have seen that sum of matrix and its transpose is symmetric. Similarly, we can write Q as half the difference of B and its transpose. Q is skew symmetric as we have seen that difference of a matrix and its transpose is skew symmetric. P plus Q is equal to B. Hence, we are able to express the original matrix B as sum of a symmetric matrix which is P and a skew symmetric matrix which is Q. Sum number 4. If A and B are 3 by 3 matrices with elements as given in the problem statement, verify the identities. A plus B whole transpose is equal to A transpose plus B transpose. A minus B whole transpose is equal to A transpose minus B transpose. In the first step, we add matrices A plus B. Then we take the transpose of the added entity, that is A plus B whole transpose. Then we add the individual transpose of A and B and show that the two resulting matrices are same. Here we continue the sum number 4. In the previous slide, we verified the first identity. In this slide, we tackle the second identity. We first subtract matrix B from A, and then we take the transpose of this entity, that is transpose of whole A minus B. Next step, we take the individual transpose of A and B. The two resulting identities are same, which verifies the second requirement of the problem statement. Sum number 5. A is a 2 by 2 matrix with the elements belonging to trigonometric functions. Verify that A transpose multiplied by A is equal to identity matrix. Solution. Taking the transpose of A and then doing a matrix multiplication with A, we get. On further simplification, we see that the LHS of the equation, after multiplying A transpose with A, is finally an identity matrix. We do a similar computation for verifying the second part of the problem statement. Sum number 6. Show that the matrix A, as given in problem statement, is a symmetric matrix and skew symmetric matrix respectively. Since A and A transpose are equal, A is a symmetric matrix. Next, we move on to the second part of the problem statement. Since A and A transpose are negative of each other, matrix A in this case, that is the second part of a problem statement, is a skew symmetric matrix. Sum number 7. Express the given matrix as the sum of symmetric and skew symmetric matrix. We know that A plus A transpose is always a symmetric matrix, and A minus A transpose is always a skew symmetric matrix. Using the above identity, we see that 2A can be represented as sum of matrices A plus A transpose and A minus A transpose. The first summation is a symmetric matrix. The second summation is a skew symmetric matrix. Computing the two matrices, that A plus A transpose by 2 for symmetric matrix and A minus A transpose by 2 for skew symmetric matrix, we get the final answer. Sum number 8. Express the given 3 by 3 matrix as the sum of symmetric and skew symmetric matrix. Symmetric part of the given matrix A will be half of A plus A transpose. The logic for this is explained in sum number 7, which is in the previous slide. Computing the value of half of A plus A transpose, we get. Similarly, applying the same logic as explained in slide number 7, skew symmetric part of the given matrix can be computed as half of A minus A transpose. The resulting elements of the skew symmetric matrix will be as is clearly evident, adding the symmetric part of the matrix A along with the zero matrix, which is the skew symmetric part, we end up with the original matrix A. Sum number 9. If A and B are symmetric matrices of same order, AB minus BA is equal to skew symmetric matrix, zero matrix, identity matrix. Solution. Given A and B are symmetric matrices, A transpose is equal to A and B transpose is equal to B. Now AB minus BA whole transpose is equal to AB transpose minus BA transpose. This is using the identity A plus B whole transpose is equal to A transpose plus B transpose. The above will be equal to B transpose A transpose minus A transpose B transpose using the identity AB whole transpose is equal to B transpose A transpose. Is equal to BA minus AB because B transpose is equal to B and A transpose is equal to A, as both A and B are symmetric. Thus, AB minus BA whole transpose is equal to minus of AB minus BA, which makes the entity skew symmetric, and option A is correct answer. Sum number 10. If A is a 2 by 2 matrix with elements cosine alpha minus sine alpha and cosine alpha, and A plus A transpose is equal to I, then find the value of alpha. Solution. Here we take I as identity matrix of order 2 by 2. The reason being LHS is a matrix of the order 2 by 2. Equating corresponding elements of the matrix, we get alpha is pi by 3. Hence, option B is the correct answer. End of class 3 on matrices.